Welcome back to the Mechanics of Solids lecture series. We're working examples calculating peak bending stress with extension to beam design. In this video, we're continuing the example we started in the last video. We've already solved for the bending moment diagram, and we have the cross-section properties as indicated here, and which we'll use to calculate the peak tensile stress and peak compressive stress along the beam. We note from the bending moment diagram that the maximum positive moment anywhere along the beam is 2,025 pound-feet, located 4.5 feet from the left end of the beam. We'll label that moment M1, and the corresponding location along the beam, location 1. The minimum moment anywhere along the beam is negative 3,600 pound-feet, which occurs right at the roller support. We'll label that moment M2, and the corresponding location, location 2. Because the cross-section is unsymmetric, we have to consider both location 1 and location 2 to determine where the peak tensile stress and peak compressive stress occurs. Let's start with compression. At location 1, since the moment is positive, the beam bends upward and the top is going to be in compression. We can calculate that stress, sigma 1 top equals M1 C top over IZ. At location 2, the moment is negative, so the beam bends downward, and the bottom will be in compression. We can calculate that stress as sigma 2 bottom equals M2 times C bottom divided by IZ. Note from the cross-section that C top is the distance from the neutral axis to the top, 2.613 inches. C bottom is the distance from the neutral axis to the bottom, or 0.787 inches. So the value, or the magnitude of M2 is larger than M1, but the value of C top is larger than C bottom. So we can't tell immediately by inspection which value is going to be larger. We need to compute them both. Our working units for stress, we want the stress in KSI, so we want to compute forces or convert forces to kips and lengths to inches. So let's go ahead and make these computations. Sigma 1 top equal to M1, 2,025 pound-feet, will convert to 2.025 kip-feet times a conversion factor of 12 inches per foot. Multiply that by C top, 2.613 inches, and divide by IZ, which is 8.13 inches to the fourth. That will give me my answer in KSI, and the value is 7.81 KSI. Sigma 2 at the bottom equals 3,600 pound-feet, or 3.6 kip-feet times 12 to convert to inches, kip inches, times C bottom, 0.787 inches, divided by the I, 8.13 inches to the fourth. This computes to 4.18 KSI. So this indicates that the first one is larger. So this will be our sigma min, or our peak or maximum value in compression. And it occurs at location 1 at the top of the beam. Right here, that's where the maximum compressive stress occurs. Start with a clean sheet for the tension. We do a similar consideration, considering both location 1 and location 2. At location 1, since the moment is positive, the bottom will be in tension. So sigma 1 bottom, M1 times C bottom over IZ. At location 2, since the moment is negative, the top will be in tension, which we can compute as sigma 2 top equals M2 times C top over I sub Z. Now comparing the two values, the magnitude of M2 is greater than M1, the magnitude of C top is greater than C bottom, So we can immediately see that this value, sigma 2 top is going to be greater than sigma 1 bottom, and we do not need to compute sigma 1 bottom. We'll just compute sigma 2 top equals M2 3,600 pound-feet, which we convert to 3.6 times 12 kip inches. Value of C top 2.613 inches divided by IZ 8.13 inches to the fourth, and that computes to 13.88 KSI, and that's our sigma max, or maximum tensile stress. And that occurs at location 2 at the top of the section. So to summarize, maximum tensile stress at location 2, maximum compressive stress at location 1, both occurring at the top of the section, and mainly due to the large asymmetry of the channel section. This concludes this example.